Good morning, everyone.
Morning, ma'am.
Morning, ma'am.
Okay, where we left in the last class, please tell me the last topic.
Ma'am, Coulomb's law and electric field intensity.
Okay. What was Coulomb's law? Does anyone remember the definition of Coulomb's law?
Ma'am, the magnitude of the electric force between two static points sensed in a vacuum is directly proportional to the magnitude of two charges and inversely proportional to the square of the distance between them and act along the line joining the charges.
Hmm. That means the force acts in a straight line, right? Yes. And the formula, do you remember the formula?
Ma'am, F equal to 1 by 4 pi epsilon naught Q1 by Q2. Q1, ma'am, F equal to 1 by 4 pi epsilon naught into Q1 by Q1 Q2 by R square.
Yes. Or you can say F equal to K Q1 Q2 by R square, right? K is 1 by 4 pi epsilon naught and K is the proportionality constant. And what about electric field? What is electric field?
Positive, a positive charge or a negative charge
Hmm.
is said to create its fields around a charge in which another charge particle experience a force is said to have the electric field in it.
Hmm. Basically, the area around a charged particle up to which it can attract or repel another charged particle. Above that particular area or beyond that area, the charge cannot act a force on another charged particle. Only the area only a particular area it can attract that particular charge or repel. Above or beyond that area it cannot act, and that particular area is called the electric field. Okay, so now today's next topic is electric field intensity. Electric field intensity at any point is defined as the force experienced by a unit positive charge placed at that point. Okay, so we know that when we put a charge particle in an electric field area, it will get attracted or it may get repelled. So what amount of intensity or what is the amount of force it will get at a particular area at any particular point, it is the electric field intensity at that particular area. See, when we come closer to the electric charge, suppose it see in case of this topics, one charge is taken as source charge and one charge is taken as test charge. Source charge can be positive charge or negative charge, but the test charge is always a positive charge. Suppose we put a source charge, positive source charge, and it because of that charge it will have an electric field area, right? And if we bring another positive charge closer to it, the test charge will get repelled because the source charge is also positive, right? But when with what amount of the force it will get repelled? Suppose when we put the test charge closer to the source charge, the amount of repulsion will be higher, right? And if we put the source charge at a distance from the Now when we put the test source at a distance from the source source, the amount of repulsion or the force will be little less than the earlier point, right? So what in electric field intensity is basically the force at a particular point of the electric field. So F equal to E equal to electric field intensity is defined by the symbol E equal to F divided by Q. Q is the charge of the test charge, not the charge of the source charge. The positive charge which we bring to test the intensity of the source charge, right? That is the Q. So Q is the charge of the test charge. So E equal to F divided by Q, or E equal to K Q by R. See, if we put the value of F in this place, F was which? K Q1 Q2 by R square, right? And so E equal to K after cancel out the see, it will be capital Q, huh? Please put this point as capital Q, the sourcer. So in the last final equation, the charge of the test charge will not be counted, only the charge of the source charge will be counted. Please keep this charge as capital Q. This will be the amount of source charge. So K Q1 Q2 by, when we put the value of F in this equation, it will be K Q1 Q2 by R square divided by Q, and cancelling out the source charge, cancelling out the value of the test charge, the final equation is K Q by R square. And this, please put this Q as capital Q. This is the amount of or this is the value of the source charge. Okay, this is the value of the source charge. This Q is the value of the test charge, but this Q is the value of the source charge. So we know the value of K equal to 9 into 10 to the power 9, huh? 10 to the power 9. This not 109, this should be 10 to the power 1. Put the 9 above 10. So the value of K is 9 into 10 to the power 9 Newton meter square divided by Coulomb square. This is the value of the uh, this is the value of the proportionality constant Q. Sorry, K, proportionality constant K. So Q is the charge of the single point source of electric. Q is the charge of a single point source of electric field, or so Q is the value of the source charge. This final Q is the value of the source charge, and R is the distance from the source charge. The distance from the source charge of the test charge. This is the value of R. So, have you understood electric field intensity, or do you have any doubt?
Ma'am,
Yes.
can you just explain again once?
Which part?
The formula part.
Okay. See, to set the electric field intensity, there will be a source charge and the source charge which electric field intensity will be tested. that is the source charge, and we will bring a unit positive charge to check the unit intensity of that source charge. That will be called the test charge. So there are two charges. So the source charge is always taken as the source charge can be taken as either positive charge or negative charge, but the test charge is always a unit positive charge. Test charge is always a unit positive charge, and the source charge may be positive, may be negative. They can be unit, they cannot be unit. That doesn't matter. But the test charge is always a unit positive charge. So when we bring the test charge near the source charge, it may get attracted or it may get repelled, uh, depending upon the sign of the source charge, right? So suppose we are taking the test charge, suppose we are taking the source charge as a positive charge and we bring a unit positive charge from outside. What will happen? That the charge will get repelled, right? And the amount of repulsion at different point of the electric field will be different due to the distance. The electric field intensity will always depend on the distance. When we bring the positive charge near the source charge, it will get highly repelled. The amount of repulsion will be very high, and if we put the charge at some distance, then the amount of repulsion will be little lower than the first one, right? So the repulsion, amount of repulsion on amount of attraction is basically the electric field intensity. So electric field intensity at a point is defined as the force experienced by a unit positive charge placed at that point. Okay, so that's why, since electric field intensity is the amount of force experienced by a unit positive charge at a given point of the electric field, that's why E equal to F by Q. This is the value of the test charge. Okay, this is the value of the test charge. Since please focus on the definition, that it is the force experienced by a unit positive charge at that point. Force experienced by this unit positive charge. Therefore, electric field intensity E equal to F by Q. See, we have already calculated the value of F, right? In the Coulomb's law part, we have calculated the value of F. What was the value of F? That F equal to K Q1 Q2 by R square. In this case, we are taking two charges. One is source charge, which we will take as capital Q, and the point charge, unit positive charge, which will be taken as small q. Therefore, the value of F will be K capital Q small q divided by R square. The value of F will be K capital Q small q divided by R square, and when we put that value in this position, the small q will be cancelled out, right? One second. This should be capital Q. Okay. Capital Q divided by R square. Okay. Let me show you the equation first. It will be like that. E equal to, if we put the value of F, what was the value of F? K Q Q divided by Q divided by R square, right? Sorry, Q divided by R square. This is the value of A. Q divided by R square, and there will be also a divided by q, sorry, not small q, divided by this q, and this q will be cancelled out, and the final equation will be E equal to k, this one, E equal to kq by r square, equal to kq by r square. This will be the final equation. This q and this q will be cancelled out. Okay, so therefore this is again capital Q. Okay, this is the capital Q is the surge of a single point source of the electric, a single point source of electric field. So Q is the capital Q is the value of the source surge. Okay, and R is the distance of the point surge from the source surge. Okay, now we have understood.
Yes, ma'am. Thank you.
Okay. Okay, next is electric lines of force. An electric line of force is an imaginary continuous line in an electric field such that tangent to it at any point given direction of the electric force at that point. The direction of line of force is direction along which a small free positive charge is move along the line. So we know that when we put the source charge and when we bring the unit positive charge, the unit positive charge may get attracted, it may get repelled according to the sign of the source charge. When it gets attracted or repelled, it will act in a straight line according to the Coulomb's law. According to the Coulomb's law, it will get attracted or repelled in a straight line. So, that imaginary straight lines which are around a charge particle or the source charge is called its electric lines of force, the imaginary lines. It will be act like from the source charge in every direction. The straight lines will be there, and the distance between the charge, distance between the electric field lines will get higher when we go away from the source charge. So the straight lines, continuous straight lines from the source charge is the lines of force or electric field lines. An electric field line is an imaginary continuous line in an electric field such that tangent to it a point. Okay, let me show you a picture of electric field lines. Okay, can you see this picture? Can you see this picture?
Yes, ma'am.
Okay.
Yes, ma'am.
Okay, so these are the lines of force due to a positive source surge and a negative source surge. See, we take the test charge as a positive charge, right? And because the test charge is a positive charge, it will get repelled in this direction. And if the source charge is negative, then the test charge will get attracted like this. In this kind of straight lines, the unit positive charge will get attracted or repelled. These are called electric field lines or electric lines of force. So see, when we go away from the source charge, the distance between the electric lines of force get bigger, and when we come closer to the source, the distance between the electric lines of force become closer. So these are the electric lines of force.
Yes.
Okay. Okay, so these are the properties of um, electric lines of force or field lines. Electric field lines originated from a positive charge and terminate on a negative charge. The direction of the electric field lines always taken as positive charge to negative charge. Number two, the number of field lines originating or terminating on a charge is proportional to the magnitude of the charge. When the charge has greater magnitude, the number of field lines will be more, and when the source charge has lower magnitude, the number of electric field lines will also be less. The number of field lines passing through a particular area will be proportional to the magnitude of electric field lines. Number of field lines passing through the see in an particular area, if that area electric field is high, then the number of field lines will be high at that particular area. Basically, electric field lines depends on the magnitude of the electric field. Two or more field lines can never intersect each other, or they cannot have multiple directions. For a particular source charge, the direction of every lines of force will be same, and they cannot intersect each other because they are going away from each other as we go beyond the electric field, right? So they cannot intersect each other. Number uh, 4 point is two or more lines cannot. No, number 5 is uniform field lines straight, parallel, and uniformly placed. Uniform field lines means in a particular area where electric field is same. So when an electric field is same, the field lines will be straight, parallel, and uniformly placed. Field lines cannot form a loop. They cannot go in round shapes, or they cannot form a loop. Field lines always flow from higher potential to lower potential. So, which is a correct point, that field lines always goes from where the electric field is high and they end at where the electric field is low. If any region electric field is absent, there will be no field lines. In the absence of electric field, there will be no field lines. These lines are imaginary lines. So, do you have any doubt? All of you have understood now these electric field lines?
Yes, ma'am.
Okay. Okay, CR, please collect the attendance. Students, give your attendance in the chat box, and CRs, please collect the attendance and give it to me. Okay, thank you everyone.